So now we're going to work through an example where we solve an indeterminate axial problem using the stiffness displacement method. So of the two methods that we learned about to solve for an indeterminate axial member, stiffness or displacement method was the first methodology that we went through. So here, just to introduce the problem, the given information that we have a steel pipe that's filled with concrete. Here I have a section view that shows the concrete's on the inside, the steel pipe is on the outside. We're given the geometry, so we know that the outer diameter of the pipe is 80 millimeters. We know the inner diameter of the pipe is 70 millimeters, and we're given the material properties for each of the materials. So 200 gigapascals for the modulus of elasticity for the steel, and 24 gigapascals for the modulus of elasticity of the concrete. And all that the problem is asking us for is the average normal stress in the steel and the average normal stress in the concrete. So to get to the average normal stress, we know that our fundamental equation is that average normal stress is equal to the internal normal force divided by the cross-sectional area. So here, a common misconception that a lot of students have is that they say, well, this column is subject to 80 kilonewtons of compressive normal force, and so I'm just going to take that negative 80 kilonewtons, that would be my internal normal force, and then I'll divide it by the area of the steel, and then I'll do another calculation. I'll take that negative 80 kilonewtons of internal normal force, and I'll divide it by the cross-sectional area of the concrete. But what that's missing is that this 80 kilonewtons of compressive force right here, it's being shared but not equally or not individually by the steel and the concrete. Some portion of that 80 kilonewtons is going to go into the steel. Some portion of that 80 kilonewtons is going to go into the concrete. And so mechanics of materials is going to allow us to figure out how much is going to go into the steel and how much is going to go into the concrete. And that will allow us to calculate the numerator of this stress equation. And so I can just write down here for the internal normal force in the steel, the internal normal stress in the steel, we take the internal normal force in the steel divided by the cross-sectional area of the steel. So we need to do a little bit of analysis to calculate this numerator. The denominator is really easy. The cross-sectional area of the steel, we're given the outer diameter, the inner diameter, so we can just calculate the area of a circle created by the outer diameter and subtract the area of the circle formed by the inner diameter. It's pretty straightforward. Likewise, we'll have pretty much the same equation for the concrete. We need to use our indeterminate analysis to solve for the internal normal force in the concrete. Again, that's not going to be the entire 80 kilonewtons of internal compressive normal force. It's going to be some component of that. And we're just going to divide it by the cross-sectional area of the concrete, which is simply calculated by the inner diameter here, because the entire inside of the pipe is filled with concrete. So we have our equation set up here. We can easily calculate the area of the steel, the area of the concrete. That's just based off these diameters. So the internal normal force is going to be where most of the work gets done in this problem. And so if you remember when we talked about the stiffness or displacement method, we have two different steps anytime that we're doing an indeterminate analysis. For the stiffness displacement method, step number one is always going to be equilibrium. So equilibrium just means statics. And again, we've already said that this is going to be a statically indeterminate problem, so we know off the bat that equilibrium isn't going to get us all the way, but it will, number one, identify that it's indeterminate. And another thing it's going to do is we have two unknowns here, the internal normal force in the steel and the internal normal force in the concrete. And this work in the equilibrium step is going to give us one equation to help solve for that. We have two unknowns, so one equation alone won't be sufficient, but it'll get us half of the equations that we need to solve for both those unknowns. Okay, so all that we need to do for the equilibrium step is I need to make a free body diagram, and I need to run the equilibrium equations to try to relate these internal normal forces. And so anytime we're trying to figure out internal forces, I need to make a section cut. And so I can just make a section cut, a cross-section cut, anywhere that I want between the top and the bottom of this column. And I guess one point of information, it's not really going to be important here because it'll end up canceling out, but I will note that the height of the column is given to us, and that's given as 500 millimeters. We'll see that's going to be inconsequential, but it was given as part of the worked out solution, so I want to make sure you have that too. So we make a section cut at any point between the top of the column and the bottom of the column. It's going to be constant internal normal forces between those 2 points because there's no intervening forces between the top and the bottom. So we can draw our resulting free body diagram. I'm going to keep the top portion of the cylinder above the section cut. Again, it wouldn't make any difference which side that I kept, because we know just based off of statics that I have an 80 kilonewton reaction here at the bottom. So my free body diagram, I'm going to keep a portion of the top of the cylinder. Here's my section cut. Before I even draw on my external forces, I'm going to draw my internal forces because, again, we just have a sign convention for the internal forces. And here, another place that a lot of students slip up is that they only draw one internal normal force and they say, okay, I just have one internal normal force here. I have my external axial force of 80 kilonewtons, and they say the internal normal force is just going to be equal to, I'm sorry, I drew that backwards, is going to be equal to negative 80 kilonewtons. But again, that doesn't capture the fact that a portion of this 80 kilonewtons is going to be carried by the steel, and a portion of the 80 kilonewtons is going to be carried by the concrete. So here we really need to have two internal normal forces. One is going to be in the steel. The other internal normal force is going to be in the concrete. Again, depending on relative stiffness, some of that 80 kilonewtons is going to go into the steel, some of that 80 kilonewtons is going to go into the concrete. If they have the exact same stiffness, it would be half and half. We'll see in this case they don't have equivalent stiffness, so one's going to carry more than the other. The other thing that I'm missing here from my free body diagram is just a basic coordinate system. Again, the direction of your coordinate system is arbitrary. It's not going to change our final answer. We just do it for convenience sake, this y-axis in line with our external and our internal forces. And now I'm just going to run equilibrium, and I'm going to sum the forces in the y direction equal to 0. Based off my coordinate system, all of my vectors pointed up. I'm going to say are positive, all the vectors pointed down. I'm going to say are negative just for purposes of summing everything up here. So my equilibrium equation becomes negative 80 kilonewtons minus the normal force in the steel minus the normal force in the concrete, all equal to 0 because it's in equilibrium. So I could rearrange this if I want to make it a little bit easier, but regardless, to say this is going to be my equilibrium equation. So I might want to solve this in terms of one of these unknowns on one side of the equation because we're going to substitute it when we solve for simultaneous equations later on. So if I wanted to, I could rewrite this and I could say the normal force in the concrete is equal to negative 80 kilonewtons minus the normal force in the steel. Or I could switch it around and I could say the normal force in the steel is equal to negative 80 kilonewtons minus the normal force in the concrete. Either way would work just fine. And we're going to take this, we're going to combine it with our second equation that we get from the next step to solve for both of these unknowns simultaneously. But again, just to point out one more time, this step shows us that it's statically indeterminate because I have two unknown forces, the internal normal force in the concrete, the internal normal force in the steel, but I only have one equation, so we can't solve for both of them with just one equation. Okay, so that's step number one. That's equilibrium, and that's the first step for the stiffness displacement method of analysis. So then step number two for the stiffness displacement method of analysis is looking at geometry, and we call it compatibility. Okay, so we're always going to draw a diagram for both of these steps, equilibrium and compatibility. when we draw a sketch for the compatibility step, I'm going to go back to my entire diagram that we had before. I don't need to make a section cut or anything like that. So I'll just draw my cylinder. And now instead of looking at forces, we're going to be looking at what we know about the geometry as it changes of this system right here. And so I want to look at the displacement of the steel and how that relates to the displacement of the concrete. So what I'm going to end up doing is I'm going to draw a green arrow here that represents a positive displacement of the steel. If we're following our sign convention, a positive displacement is going to be elongation. We know that at the support at the bottom of the cylinder that there's going to be no displacement. That's the definition of our support. And so if the steel has a positive deflection or positive displacement, that's going to be elongation, which means that, say, the point up here at the top of the cylinder is going to have to go upwards. So let's say the deflection of the steel, a positive deflection of the steel, means this point at the top of the cylinder is going to be moving up. And so, for example, if this point in the steel moves up 1 inch, what's the displacement in the concrete going to be? What does it have to be? And here, I mean, one of the assumptions, and maybe we could write this down, would be that the steel and the concrete are bonded to each other. That's an assumption. We could write it down, or maybe it's in part of the problem statement. But a big assumption here is that this interface between the concrete and the steel is such that they're bonded together. And so if the steel displaces, let's say, positive 1 inch, the concrete also has to displace that same amount. So whatever the displacement in the steel is, a positive displacement of the steel is going to be exactly equal to a positive displacement of the concrete. They'll have the same magnitude, the same direction. So then simply the beginning of my second equation, my compatibility equation, is based off this really straightforward diagram here, and it simply says that the displacement of the steel is equal to the displacement of the concrete. Sometimes in your book they'll say this is the compatibility equation. We kind of stop right there. I'd like to take it a little bit further, because the whole point is that our compatibility equation, when combined with our equilibrium equation, is going to give us the two equations to solve for our two unknowns, which is the normal force in the concrete and the normal force in the steel. So all that we're trying to do is take this displacement and relate it back to the internal normal forces. So the way that we do that, we know that this system right here, we've already done some free body diagrams, and we know that, well, our fundamental equation, let's back up a little bit, for the displacement of an axial member is the integral over the length of the internal normal force as a function of x dx divided by the cross-sectional area as a function of x times the modulus of elasticity. So our fundamental equation is generally applicable. But in this case, we can simplify this down quite a bit, because we know that the internal normal force for this type of loading is going to be constant. So this internal normal force is just going to be a constant n. The cross-sectional area we see is prismatic here from the top of the cylinder to the bottom. And so A of x is simply going to be a constant value A. So we can simplify this general equation down and just say that any of the displacements of either the steel or the concrete is simply equal to the internal normal force times the length divided by AE. And so I can rewrite both sides of this compatibility equation, and I'll say NL over AE of the steel is equal to NL over AE of the concrete. So we could say that this is our equation number 2, right? We have equation number 1 up here. We have equation number 2 down here. We can even simplify this a little bit more if we want to. Like I said before, it took me until going through the problem to even talk about the length of this column. But we notice that the length of the steel is the same as the length of the concrete. And so in terms of this equation, we can simply cancel out the length of each of these columns. Just because they're both the same there's no difference in relative stiffness between the steel and the concrete due to their length. There'll be changes in relative stiffness due to the cross-sectional area and the modulus of elasticity, but the length cancels itself out. So I could simplify this a little bit more if I wanted to, and I could say that the normal force in the steel divided by the area of the steel times the modulus of elasticity of the steel is equal to the normal force in the concrete divided by the area of the concrete times the modulus of elasticity of the concrete. All right, so maybe this is a better equation number 2 because we drop out the L. Just saves a little bit of work. Okay, so now I have these two equations. There's only two unknowns, and they share the same unknowns between the two equations. The normal force in the steel and the normal force in the concrete. So I'm just going to solve those two simultaneously. All that I really need to do is take one of these equations where in the equilibrium equation where I've set it equal to one of the unknowns. So for example, here in the top equation, this on the right is equal to the normal force in the concrete. So I'm simply going to take that and I'm going to substitute it down at the bottom wherever I have a normal force in the concrete. So at that point, this numerator is going to become, instead of the normal force in the concrete, it'll become negative 80 minus the normal force in the steel. And the resulting equation is only going to have one unknown, which is the normal force in the steel. So I can rewrite that if I have some space. So step number 3 here is I could just say solve equations 1 and 2 simultaneously. So I'm going to take this equation, the left side's not going to change. But the right-hand side, I'm going to substitute in this negative 80 minus the normal force in the steel for the normal force in the concrete. All divided by the area of the concrete, modulus of the concrete. So again, I only have one unknown in this combined equation. I need to fill in the values for the area of the steel, for the modulus of elasticity of the steel. I need to fill in the area of the concrete, the modulus of elasticity of the concrete as well too. But at that point, it's just some basic algebra. Okay, so let me erase a little bit and I'll start plugging in those values. So again, simply taking this equation, we'll start back up at the top. The internal normal force in the steel, we don't know that. That's the unknown, one of the unknowns that we're solving for. All right, the area of the steel, the area of a circle is simply pi over 4 times the diameter squared. Here, the outer diameter is 80 millimeters. So I'll do 0.08 meters squared. But we have to subtract out the inner diameter because it's a pipe, so the inner diameter isn't steel. So we subtract out the inner diameter, which is 70 millimeters or 0.07 meters. All right, so this entire term right here is going to be the area of the steel, the modulus of elasticity of the steel. That's what we looked up in the back of the book when we were told it was A36 steel. That's simply 200 gigapascals, or in other words, 200 times 10 to the 9th pascals. All right, is equal to, we have negative 80 kilonewtons. I'm going to change that to negative 80,000 newtons. Or negative 80 times 10 to the 3rd newtons minus, I'm sorry, this should be the normal force in the steel. All right, minus the normal force in the steel. Okay, divided by the denominator is the area of the concrete. So we have pi over 4 times the inner diameter, which defines the outer diameter of the concrete annulus. So that's 0.07 or 70 millimeters. Square that term. And the modulus of elasticity of the concrete. And that was given to us as 24 gigapascals, or 24 times 10 to the 9th pascals. Again, we only have one unknown in this equation. That's the internal normal force in the steel. I do some algebra. I'm going to gloss over that. I get that the internal normal force in the steel is equal to negative 57.47 kilonewtons. Okay? So that's telling me that about 2/3, maybe 3/4 of this 80 kilonewtons is going to be carried by the steel. All right, so that's over half of the load is going to be carried by the steel. And so it's kind of hard to tell whether or not that's reasonable. We know that the length of the steel and the concrete cancels out, so that's not going to make any difference in stiffness. We know the modulus of elasticity of the steel is much larger than the modulus of elasticity of the concrete. So that alone tells us that the steel should be carrying more, just that one factor, almost 10 times as much here. But if we were to calculate out the area of the steel versus the area of the concrete, we'd see we have much larger area of the concrete. So the material properties tell us that the steel should carry more. The area alone tells us that the concrete should carry more. And this is simply telling us that the stiffness of the material is kind of outweighing the stiffness based off cross-sectional area. But it seems like a pretty reasonable number. It's not like 99% of the load is being carried by the steel or 1% is being carried by the steel. It seems like a good ballpark number. So it passes the reasonableness test. And now if we want to figure out what the internal normal force in the concrete is, then we can just use equilibrium again if we want to. We erased our free body diagram to calculate equilibrium, step number 1 that we looked at. But we know that the internal normal force in the concrete is equal to negative 80 kilonewtons minus the internal normal force in the steel. So we just calculated the internal normal force in the steel, so we can plug that into this equation. I still have the negative 80 kilonewtons right here, but I get minus negative 57.47 kilonewtons. And so we end up getting the internal normal force in the concrete is equal to negative 22.53 kilonewtons. Again, both of those added up has to be equal to the negative 80 kilonewtons, which works out. Okay, so I have the internal normal force in the concrete. I have the internal normal force in the steel. That gets me most of the way to calculating the normal stress in each of those elements. So my last step, now that I've solved for the internal normal forces, is to simply solve for the internal normal stress, which is the very first equation that we looked at right here. So we'll just say that's step number 5. And the average internal normal stress in the steel is equal to the normal force in the steel divided by the area, the cross-sectional area of the steel. So normal force in the steel is negative 57.47 times 10 to the 3rd newtons, divided by the cross-sectional area of the steel, which is this portion of the denominator up here, pi over 4, times the outer diameter squared, 0.08 meters squared, minus the inner diameter squared, which is 0.07 meters squared. And we get that the average normal stress in the steel is equal to negative 48.78 megapascals. Okay, this is going to be one of our final answers. Our next normal stress equation is just going to be for the concrete. And we get the normal stress in the concrete is equal to the normal force in the concrete divided by the area of the concrete. We already calculated the normal force in the concrete. as negative 22.53 times 10 to the third newtons. The denominator is the area. We have the formula for that up here. Pi over 4 times the diameter squared. Pi over 4 times 0.07 meters squared. And I get that the normal stress in the concrete is negative 5.85 megapascals. All right, here's my other final answer. So the two boxed solutions down here are my final answers. That's the normal stress in the concrete and the normal stress in the steel. So one thing that I talked about in lecture, and one thing that we actually use quite a bit in our design calculations when we're doing especially reinforced concrete beams. If you take a concrete design class, or just even any composite beam, a common calculation or ratio that we use is called the modular ratio. So the modular ratio is just lowercase n. It's equal to the modulus of elasticity of one of the materials divided by the modulus of elasticity of the other material that makes up a composite. And this modular ratio is also going to be equal to the normal stress in that first material divided by the normal stress in the first material. This assumes that they both have the same length, okay? So just like this, both those materials are occupying the same length. All right, so they both start and they end at the same location. That's an assumption that we make here. But for a composite beam, things like that, that's almost always going to be the case. And so we can notice here that if I plug in the modulus of elasticity values, 200 divided by 24, if we have steel on the top and we have concrete on the bottom, that's the same as the ratio of the normal stress in the steel, which is negative 48.78 divided by negative 5.85. And I believe that same value is simply 8.33 in this situation. So that's what we would call the modular ratio. And it helps, like I said, in design calculations when we're looking at composite beams, composite columns is a common design value that we use, lowercase n, for the modular ratio.